What specific problem does the proposed self-rewarding reasoning framework aim to solve in the context of large language models?
The proposed self-rewarding reasoning framework aims to address the limitations of intrinsic self-correction in large language models, LLMs, particularly their inability to effectively refine initial responses without external feedback. Current LLMs struggle to detect and correct errors in their self-generated outputs, leading to reduced accuracy in reasoning tasks. By integrating the generation and evaluation capabilities within a single LLM, the framework enables models to autonomously generate step-by-step reasoning paths, evaluate their correctness, and revise responses based on self-generated reward signals. This approach simplifies the decision-making process and reduces computational overhead compared to traditional methods that rely on external reward models. Ultimately, the framework enhances the model's self-correction abilities, leading to improved performance in mathematical reasoning tasks.
Can you explain how the self-rewarding reasoning framework works? Illustrate the methodology step by step, particularly focusing on the two-stage framework and the processes involved in each stage.
The self-rewarding reasoning framework operates through a two-stage methodology designed to enhance the reasoning capabilities of large language models, LLMs. In the first stage, known as self-rewarding instruction following fine-tuning, IFT, the framework utilizes sequential rejection sampling to generate long chain-of-thought (COT) trajectories that incorporate both self-rewarding and self-correction behaviors. This involves generating initial reasoning responses, evaluating them, and collecting data on correct and incorrect responses to fine-tune the model, enabling it to learn to detect and revise errors in its outputs. In the second stage, reinforcement learning (RL) optimization is applied to further refine the model's ability to assess correctness and improve its responses. This stage leverages rule-based signals to enhance the self-rewarding patterns established in the first stage, allowing the model to iteratively improve its reasoning through self-evaluation and correction. The combination of these two stages results in a unified framework where the model autonomously generates, evaluates, and corrects its responses, significantly improving its reasoning performance compared to traditional methods that rely on external reward models.
Could you provide a simple, illustrative example that demonstrates the inner workings of the self-rewarding reasoning framework during a self-correction task?
In the self-rewarding reasoning framework, the process begins with an initial prompt, such as a mathematical problem. For example, the model generates an initial reasoning attempt, say the answer is 5. It then evaluates this response, producing a self-evaluation like verify wrong if the answer is incorrect. Upon receiving this feedback, the model generates a refined response such as the answer is actually 7 and evaluates it again. If this new response is assessed as correct, the process terminates. Otherwise, the model continues to iterate, generating further refinements until it reaches a self-evaluation indicating correctness. This iterative process exemplifies how the framework integrates generation, evaluation, and correction within a single LLM, allowing it to autonomously improve its responses based on self-generated feedback.
What are the key theoretical and practical benefits of your proposed method compared to traditional self-correction approaches that rely on external reward models?
The proposed self-rewarding reasoning framework offers significant theoretical and practical advantages over traditional self-correction methods that depend on external reward models. Theoretically, it unifies the generation and evaluation capabilities within a single LLM, simplifying the decision-making process and reducing computational overhead, as opposed to requiring multiple models during inference. Practically, our method demonstrates superior performance in self-correction, achieving higher accuracy in correcting errors while maintaining correct responses, as evidenced by improved metrics such as delta I to C, T_1, T_2, and lower delta C to I, T_1, T_2, compared to traditional approaches. Additionally, the self-rewarding framework allows for autonomous evaluation and correction without the need for external ground truth feedback, which mitigates the risk of reward hacking and enhances efficiency in inference by terminating early when the model is confident in its responses. Overall, these benefits lead to a more effective and resource-efficient self-correction process in reasoning tasks.
How was the self-rewarding reasoning framework validated and tested? Please elaborate on the datasets used, experimental design, and metrics for performance evaluation.
The self-rewarding reasoning framework was validated through extensive experiments using standard mathematical reasoning benchmarks, specifically Math 500, Olympiad Bench, and Minerva Math. The experimental design involved a two-stage training approach. First, self-rewarding instruction following fine-tuning, IFT, was conducted using a dataset of 32K trajectories collected via sequential rejection sampling, followed by reinforcement learning, RL optimization, to further refine the model's ability to assess correctness and improve responses. Performance evaluation metrics included the accuracy of the first attempt, final accuracy, and improvements in accuracy from the first attempt to the final answer, specifically measuring transitions from incorrect to correct and vice versa. The results demonstrated that self-rewarding reasoning models significantly outperformed existing baselines, achieving higher final accuracy and better correction capabilities, as evidenced by metrics such as delta T_1 T_2 and delta I to C T_1 T_2. Additionally, the model's ability to recognize correct trajectories was assessed, showing that the self-rewarding IFT model achieved over 90% accuracy in identifying correct responses, further validating the effectiveness of the framework.
What limitations or potential drawbacks did you identify in the proposed self-rewarding reasoning framework? How do these limitations impact its practical implementation or the results achieved?
The proposed self-rewarding reasoning framework has several limitations that impact its practical implementation and results. Firstly, while the framework integrates the generator and reward model into a single LLM, it still exhibits challenges in accurately recognizing incorrect responses, as evidenced by the lower accuracy in identifying wrong trajectories compared to external reward models. This discrepancy suggests that the self-rewarding model may struggle with out-of-distribution issues, which can hinder its performance in diverse scenarios. Additionally, the framework's reliance on self-generated data for training can lead to stability issues, as observed in the ablation studies where the model's ability to self-correct was inconsistent. Furthermore, the models tend to become overly conservative in modifying correct answers when faced with misleading rewards, which can reduce the overall correction rate. These limitations highlight the need for careful consideration of data composition and reward signal design to enhance the framework's effectiveness in real-world applications.